I've had a few questions from people about how to solve these problems of objects moving on inclines or on ramps. So I thought I'd set up one more example problem for you to help you finish up that homework and get some practice with this. So in this situation, we've got a block being pulled up a ramp with this 55 Newton force. And so we know that without that force, gravity acting straight downward would have some component that's trying to drag it back down the ramp. It also tells us here that we've got friction involved in this case. We need to identify where that friction is, which direction that's acting. Ultimately, we're looking for the coefficient of kinetic friction, so we're looking to solve for mu. So in any of these problems, any problem involving forces, or really any problem in physics, now that we're to the more advanced multi-step problems, a good place to start is just writing down the variable that we're trying to get to at the final, at the very end, and pick out some equations that we could use to get there. So if we're looking for mu k, there's only one equation that appears in. That's the force of friction, kinetic, is equal to mu k times the normal force. So in order to solve for mu k, I need to find the kinetic friction force and the normal force first. So now that I know I'm looking for forces, that tells me, okay, well I probably need to do something with a free body diagram and those Newton's second law equations. So draw out our free body diagram as our next step. In this case, we've got, let's see, that 55 Newton force is going up the ramp. 55 newtons, that's the applied force. Normal force is always perpendicular to the ramp, so that'd be up like this, Fn. Gravity is always straight down toward the center of the Earth, Fg. And then friction is always going to act parallel to the ramp, opposite the direction of motion. So it says the block's being pulled up the ramp. That must mean that friction is pointing back down the ramp. Okay, so in order to solve this, I need to get values for the frictional force and the normal force. Now we talked in class about how with these free body diagrams, everything is kind of off the axes if we think of our axes as looking like this, with x being horizontal and y being vertical. I see that the 55 newtons, that has an x and y piece. The normal force has an x and a y piece. The frictional force has an x and a y piece. My acceleration up the ramp is going to have an x and a y piece. And then only gravity has just a single component. So it's kind of a pain to use this system. So we don't. We get rid of this, and instead we're going to use the system where y is going to be perpendicular to the axis. That'll be y. And x will be parallel to the surface. And I didn't draw that very well. Let me try that again. Yep, same mistake. There we go. So this is our x-axis then. So basically we're just tilting our head on this problem. You might find it useful now to note that the 55 newtons, that's only in the x direction, as is the frictional force. The normal force is only in the y direction. The acceleration will be only in the x direction now. And it's just this gravitational force that has an x and a y piece. So let me clean this up a little bit. We'll redraw our force of gravity as having a y component there and an x component like this. So this will be force of gravity in the y, this is force of gravity in the x, and this is just the force of gravity overall. So now at this point we know that we're looking for the normal force and the frictional force. And so I have the normal force in the y direction. That tells me I need to do net force in the y direction, that equation. So over here, net force in the y direction is going to equal mass times the acceleration in the y. And in the y direction, the direction that's perpendicular to the ramp here, we don't have any motion. No motion, no velocity, no acceleration, nothing's going on in the y direction. So acceleration in the y is just going to be 0. So the net force in the y, that just means we add up all the forces that act in the y direction. That's our normal force, upward, and then this downward gravitational y component. Okay, so our normal force is equal to the y part of gravity. They're just in opposite directions. So that tells me I need to figure out what the y part of gravity would be in order to get to normal force, which I need to plug into this equation at the very end. So gravity, we have a special equation we can use with. Force of gravity is equal to the mass times the acceleration of gravity, which in this case was 12.5 kilograms times 9.8 meters per second squared. And so the force of gravity here is equal to 12.5 times 9.8, 122.5 newtons. Okay, so that's right here. But I don't want the overall gravity right now, I want the y component of the gravity. Well, this ramp is rotated 20 degrees from horizontal. Normally, gravity points straight down along the y-axis, but because the ramp is rotated 20 degrees, our y-axis has been rotated 20 degrees as well. So I know that this angle right here is 20 degrees also. It's 20 degrees away from the negative y-axis. So if I want the force of gravity in the y direction, I need to do the force of gravity, the overall, that's the hypotenuse of this triangle, times the cosine of 20.0 degrees. So 122.5 times the cosine of 20 degrees. There we go. Cosine of 20 degrees is 115.1 newtons. So I can come back up here, normal force, gravitational force in the y direction, those are both equal and they are 115.1 newtons. Okay, now in the equation for the coefficient of friction, I had the normal force that I needed to find, which I've done, so that part's good, and I've got the kinetic frictional force that I need to find. I see that that's a force in the x direction, so that means I also need to do my net force in the x direction. Separate this. It's equal to mass times acceleration in the x direction. Now in the x direction, I've got three forces. I have this 55 newtons forward, I've got the frictional force backward, and I've got the x part of gravity acting backward. So that's 55 newtons minus the force of friction minus the x part of gravity. And that's equal to mass times acceleration in the x. And I can fill in a little bit more there. 55 newtons minus the force of friction minus, well, the x part of gravity I can figure out using trig again. That's in this right triangle. It's opposite of the angle over there, so FG in the x direction is going to be equal to FG times the sine of 20.0 degrees. So that's 122.5 newtons times the sine of 20 degrees, which gives us 41.897 newtons. So we can plug that in here, 41.897 newtons, and that's equal to our mass, 12.5 kilograms, times the acceleration, which was given as 0.55 meters per second squared. I'm out of room there. Okay, so now I've got frictional force is the only variable in this equation. so we can rearrange to solve for it. So I've got 55 newtons here minus the frictional force, 55 newtons minus, actually let's combine those two terms, those two constants, so 55 minus the 41.897, that gives us 13.10 minus the force of friction is equal to the 12.5 times the 0.55, gives us 6.875 newtons. Okay, so we'll add the force of friction to both sides. And then subtract the 6.875 newtons. And we get the frictional force by itself over here. And that's equal to the 13.1 minus the 6.875, and we get 6.225 newtons. Okay, so now I've solved for the normal force and the frictional force here, so I can plug that back in to get mu k. So if I rearrange the equation, mu k is equal to the force of kinetic friction divided by the normal force, which is going to be 6.225 newtons, divided by our normal force, which was 115.1 newtons. Okay, so the 6.225 divided by 115.1, and we get 0.054. So a very slick ramp then, I guess. Alright, so the process here is, it's a little lengthy, for sure, but it's always about the same. Start out by finding an equation that has the ultimate goal variable in it, and then use that to figure out what you need to solve first. So I'm looking for mu k. It appears in this equation. Before I can solve it, I knew I needed to find the normal force and the frictional force. We're always going to be dealing with forces in these problems in this chapter, so free body diagrams are always a good idea. That helps me to see that, normal force is in the y direction, frictional force is in the x. Then I knew I had to do my Newton's second law equations in both directions to solve those to get to my ultimate answer here. Rotating the axes like this, that's a big help in problems where we're on an inclined plane, so keep that in mind. You don't have to do it that way, but it does save a lot of calculation and a lot of places to make mistakes. So I definitely recommend that. If you prefer, you can just redraw this image with everything rotated counterclockwise a little bit so that gravity points off to the left by 20 degrees and everything else points straight up or straight left or straight right. So that does help some people, I know. If you have further questions on this, please don't hesitate to send me an email, and I'll be glad to help you work through these problems.